Okay, so welcome to this video. In this video, what we're going to talk about is we're going to have a basic introduction to transporters. Okay, so we're going to see what the difference between a transporter and a channel is. Okay, right, so the structure for this video then, what we're going to start off with is a discussion of the need for exchange of solute across the cell membrane. Okay. Then what we're going to talk about is diffusion, and we'll talk about chemical gradients, electrical gradients, and then we'll build this up into electrochemical gradients. And then we'll talk about the fact that the cell membrane presents a significant challenge to cross if you are a polar molecule. And then we'll discuss the solution to this, which is through having channels in the membrane and also these things called transporters. And we'll see what the difference between a channel and a transporter is. We'll then discuss the difference between passive transporters and active transporters, and then the difference between primary active transporters and secondary active transporters. Okay, so let's start with the very basic motivation for the entire subject, okay, which is that we need exchange across the cell membrane. So let's draw a cell here, okay, so this is the cell membrane, this circle here, and then this is the cytoplasm here. We'll have the nucleus of the cell inside there, and then we've got the extracellular fluid surrounding it. Basically, the blood is making sure that there is a constant delivery of raw materials into the extracellular fluid. Okay, so we've got some raw materials here. Okay, and you can think of these as, for instance, oxygen molecules and glucose molecules and other raw materials. And we need to get these raw materials into the cytoplasm of the cell, where processes such as energy metabolism will occur and also biosynthesis. Okay, so we're going to use these raw materials potentially to generate energy. Okay, so we might break them down to release energy, and the fancy word for breaking things down is catabolism. Okay, and we can also use raw materials to build bigger molecules such as proteins and DNA and large biological molecules like that. Okay, so we can also use them in biosynthesis. And the fancy word for building molecules is known as anabolism. Okay, so if you're making something, if you're building something rather than breaking something down, that's called anabolism. So anabolism means taking small things, joining them together to make something bigger. Catabolism means taking a big thing and then breaking it down into even smaller pieces. And both of these together, the combined term for anabolism and catabolism is metabolism. Okay, so metabolism really just means the chemical reactions which are occurring within a cell. Okay, right, so we're bringing in the raw materials to do these two types of chemical reactions, catabolism and anabolism. Okay, so we're going to metabolize the molecules, and metabolism will produce then some byproducts. Okay, so some nasty products that we don't want to build up inside the cytoplasm of the cell. Okay, and we therefore need these byproducts to be excreted from the cell, to move out of the cytoplasm and into the extracellular fluid and be carried away by the blood. Okay, and examples, of course, are carbon dioxide and things like that. Okay, right. So that's the basic motivation for we need to be able to get molecules across the cell membrane, basically. Now, let's talk about diffusion. Okay, which is the process whereby things will move. Okay, right, so let's imagine that we have two simple compartments. So rather than drawing it with cells, we'll go now to a simpler diagram where we've just got squares. Okay, so we've got two compartments separated by a membrane here. So I'll colour this membrane in red here. And this is analogous to the cell membrane, basically. Although we've got this side of the container, which you can imagine is made of glass, if you like, the basic principle that we have two compartments, an intracellular compartment and an extracellular compartment, is still the same, basically. Okay, so if you have a very high concentration of a solute on one side, Okay, and by the way, solute just means some sort of molecule that is suspended within water, okay, which most of our biological molecules are going to be. Okay, so solute. So if you've got some sort of solute that is at a very high concentration in one compartment, and then you've got a very low concentration in the second compartment. So let's call this compartment 1, and we'll call this compartment 2 here. Okay, then basically we all know that if this membrane is permeable to the solute, i.e. if the solute can somehow get across the membrane into the other compartment, what will happen is that over time these two concentrations will equilibrate, basically. Okay, like so. So you'll end up with a roughly equal concentration in each of those two compartments. Okay, and this occurs because if the membrane is permeable, then we can think about the number of solute molecules which will be crossing from compartment 1 to compartment 2 at any time. Okay, so let's say we watch the membrane for a second and count all of the solute molecules that move from compartment 1 to compartment 2. We'll get some sort of number. Okay, we can also then count the number of solute molecules that move from compartment 2 to compartment 1 in that same second. And of course we'll find that the number that moved from compartment 1 to compartment 2 is bigger than the number which moved from compartment 2 to compartment 1, simply because the chance of a solute molecule hitting the membrane from this side and going through is much smaller than the chance of a solute molecule hitting from this side and going through this way. Okay, so this means that when you work out the net movement of solute across this membrane, you're going to get a net movement in this direction. So all you need to do is take the movement from 1 to 2 and subtract off the movement from 2 to 1. Okay, and that means that in that second you have overall moved molecules from compartment 1 to compartment 2, and this will continue happening until you finally reach an equilibrium, which will be at the point when the number of solute molecules which hit the membrane from this side and go into compartment 2 is equal to the number of molecules which hit the membrane from compartment 2 side and go into compartment 1. So when the rate of movement from 1 to 2 is equal to the rate of movement from 2 to 1, then you reach what is known as a dynamic equilibrium. And the reason it's called a dynamic equilibrium is that overall there is no net movement of solute molecules across the membrane, even though there are still molecules moving across the membrane. It's just that the number moving from compartment 1 to compartment 2 completely matches the number that moved from compartment 2 to compartment 1. Okay, so there's no net change. Right, okay, so that's the concept of a chemical gradient, and that is capable of driving the movement of molecules across a membrane. Okay, right. So I just want to raise a little point with you here, okay, because this is generally not what people would consider energy, okay, but there is a sort of energy held within this conformation here. Okay, because how do you define energy? Well, usually people define it as the capacity to cause change. Okay, so this gradient of molecules that we initially had here, this chemical gradient as it's called, which was the concentration gradient across this membrane here, this does have a form of energy held within it because it does have the capacity to drive change. Once you press start, and you put that membrane within that's permeable, then it will change the structure of this apparatus over time, basically. So it does drive a change, and therefore you would consider there to be energy stored in the fact that there is a much higher concentration of solute molecules here than there is here. Okay, so just something to think about there, and that's going to be an important concept, that concentration gradients like this do have an energy stored within them. That's going to be an important concept when we want to merge chemical gradients with electrical gradients to come up with electrochemical gradients. Okay, so we would say that the chemical potential here was higher than the chemical potential here. Okay, and that's why you're getting this net movement of these molecules from compartment 1 to compartment 2, because they're moving down the chemical gradient. Okay, right. So that's the concept of chemical potential, and it's just really talking about the concentration of the molecules. And you should think about it having an energy stored within this conformation that has been released when you move it to this conformation. Okay, right. So now let's talk about electrical gradients that we can have across cell membranes, or membranes, because these are also going to be responsible for moving solutes. Okay, so if we start this time with an apparatus that has completely even concentrations, okay, so there is no chemical gradient this time across the cell membranes. The chemical potential of this side is completely the same as the chemical potential of this side, okay, so I'll try and get these to look reasonably similar. Okay, there we go, and I'll draw the membrane once again in red down the middle here. Okay, but this time what we're going to create is an electrical gradient across the cell membrane. Now, for these solute molecules to care about an electrical gradient, they themselves are going to have to be charged. If they're neutral, they don't care whether there is an electrical gradient across the cell membrane. So let's say that these molecules have a positive charge. So maybe we'll call them sodium ions. Okay, so let's say that these blue dots represent sodium ions that are dissolved within the water. Okay, we're now going to create what's known as an electrical gradient across the cell membrane. Now, basically, electrical potential is a concept from physics, okay? And this is what you do. It is a mathematical model to help us understand reality. And the model is this: to every point in three-dimensional space, you ascribe a real number, okay? Now this real number could be positive, it could be 0, it could be negative, okay? And this is going to be the electrical potential at that point. So if I draw a little three-dimensional graph here, to every single point in three-dimensional space, you are going to ascribe this number, which is going to be the electrical potential of that point. And the units of electrical potential are volts. Okay, so every point gets this electrical potential in volts. Okay, now let's say that all of the points on this side of the membrane here are in electrical equilibrium with one another and have the same electrical potential. Okay, so if we had a little man, like so, who has a machine which can measure electrical potential at any point, he can go around this entire compartment here, he can move around the entire compartment, and wherever he stands he will get the same number. Okay, so let's call this compartment 1 again, and this compartment 2. Okay, so let's say that the number that his machine shows, we'll call that E1. The capital E is for electrical potential, and then the 1 denotes that we're talking about compartment 1. So he can go anywhere in this compartment, and he will have the same number appearing on his screen, which is the electrical potential of compartment 1. Similarly, let's say that compartment 2 is completely in electrical equilibrium. Okay, so if this little man goes into compartment 2 and moves around anywhere within that compartment, he will get the same readout on his machine. Okay, so we'll say that this is the electrical potential of compartment 2. So all of the points in compartment 2 have the same electrical potential, and we're going to denote that capital E for electrical potential, and then subscript 2 for within compartment 2. Okay, now let's say that the electrical potential of compartment 1 is not the same as the electrical potential of compartment 2. Okay, so across the membrane there is then the concept of an electrical potential difference. Okay, so electrical potential difference is also called voltage, and it's usually denoted V. So let's say we want the voltage from compartment 1 to compartment 2, and strictly speaking, when people talk about voltage, they should tell you exactly which 2 points they're going between, because we are saying that all of the points of compartment 1 have the same electrical potential and all of the points of compartment 2 have the same electrical potential. We don't need to do that. I can just say the electrical potential difference between some arbitrary point in compartment 1 and some arbitrary point in compartment 2, and it's not going to matter which arbitrary point in compartment 1 I pick and which arbitrary point in compartment 2 I pick. Okay, but importantly, they should tell you the direction you're going. We are going from the point in compartment 1 to the point in compartment 2, and people rarely bother to do that. Okay, they'll just say the electrical potential difference across the cell membrane. They should, strictly speaking, tell you exactly which direction they're going in. All it will change if they don't tell you which direction you're going in and then you pick the wrong direction that they didn't mean, is it will flip the sign of the electrical potential difference. But it's still nicer if they do tell you exactly which direction they're going in. Okay, right. And when we're talking about the electrical potential difference across the cell membrane, we always mean from the extracellular compartment to the intracellular compartment. Okay, so you're always going in that direction there. Okay, right. So, let's say that there is an electrical potential difference across this cell membrane, and shall we say it's a size of plus 60 millivolts. Okay, so a millivolt just means 1,000th of a volt. Okay? Right, so what does this mean? Well, let me tell you first exactly what the electrical potential difference across the cell membrane from compartment 1 to compartment 2 means. This means if the little man with this clever machine stood in compartment 1, okay, and measured the electrical potential there, he would get some number on his screen, and that number would be this number here, E1. Okay, if he then went and stood in compartment 2, and again measured the electrical potential within compartment 2, he would get a number on this screen, and that number will be E2. Okay, the electrical potential difference from compartment 1 to compartment 2 means how much does the number on his screen change when he moves from compartment 1 to compartment 2. Okay, so let's think about how this would actually appear in the form of an equation. Okay, so we're asking how much would the number change when I move from compartment 1 to compartment 2? Well, this means the new electrical potential, so the new number on his screen, the number after he's moved, which is of course the electrical potential of compartment 2, subtract the old electrical potential that was on his screen before he'd moved, so subtract E1. Okay, so this is what is meant by the electrical potential difference from compartment 1 to compartment 2. It tells you how much the electrical potential changes when you move from compartment 1 to compartment 2. Now, this will have the same units as electrical potential itself. The units of electrical potential were volts. We're just subtracting one electrical potential from another electrical potential, and therefore you're going to maintain the same units. So the units of electrical potential difference, or voltage, are again volts. Okay, right. So a millivolt then just means 1,000th of a volt. So this is really telling us that the electrical potential difference across the cell membrane, or the membrane, from compartment 1 to compartment 2 is plus 0.06 volts. Now, what does that mean? That means that when I go from compartment 1 to compartment 2, the electrical potential goes up, and it goes up by 60 millivolts, basically. So compartment 2 has the greater electrical potential, and it's greater by 60 millivolts. Now, even though there was no concentration, or there was no chemical gradient across the cell membrane, we've now got this electrical gradient across the cell membrane, because the electrical potential of all of these points is not the same as the electrical potential of all of these points. We said that this solute was positively charged. It was sodium ions. Okay, sodium ions are going to want to be in the compartment with the lower electrical potential, which is currently compartment 1. Okay, right. So what's going to happen is the sodium ions are going to feel a sort of pull into compartment 1, okay, from compartment 2. So if we actually look at how many sodium ions are going to move from compartment 2 to compartment 1, we'll find something potentially like this. And if we look at how many sodium ions are moving from compartment 1 to compartment 2, we might find something like this. And the reason these are not equal, even though the concentrations on either side are equal, is because the sodium ions on this side are they want to stay here, okay? So the probability that they are going to hit the membrane is reduced by the electrical potential difference across the cell membrane. In addition, the sodium ions on this side, they want to get into compartment 1, so they're going to have an increased probability that they're going to move across the cell membrane than if there was no electrical potential difference across the cell membrane. So you're going to raise the movement from compartment 2 to compartment 1, and you're going to reduce the movement from compartment 1 to compartment 2, compared to if we hadn't got any sort of electrical potential difference across the cell membrane. And therefore you're going to get a net movement of sodium ions from compartment 2 to compartment 1, even though there is no concentration gradient. So electrical gradients can also influence the movement of ions across membranes. And of course, what will gradually happen is you'll move some sodium ions back onto this side, okay? So because we've got a net movement of sodium ions now, sodium ions are going to move from compartment 2 into compartment 1. So let me show you the updated picture for this. Okay, and we'll discuss when we're actually going to get to a dynamic equilibrium now. Okay, so now we need a greater concentration of sodium ions in compartment 1 compared to compartment 2, because as I say, because of the electrical gradient, we're going to get a net movement of sodium ions into compartment 1. Okay, so I'll try and show this. So, there we go. We've got now a greater concentration on the side of compartment 1 compared to the side of compartment 2. Now, what's the effect of moving these sodium ions? Well, firstly, it means that now the concentration in compartment 1 is greater than the concentration in compartment 2. Okay. In addition, sodium ions carry a positive charge. Positive charge is going to affect the electrical potentials across the cell membrane. When we move sodium ions out of compartment 2 and into compartment 1, we are adding in more positive charge into compartment 1. So the electrical potential of compartment 1 will go up, because where you put positive charge, that raises the electrical potential of that area. So the electrical potential in compartment 1 will go up. Meanwhile, because we are removing positive charge from compartment 2, you're going to be reducing the electrical potential in compartment 2, because remember, the positive charge that was there initially in the form of these sodium ions was helping to keep the electrical potential high. Once you've moved that away, that's going to result in the reduction of the electrical potential there. Okay, so taking the positively charged sodium ions out of compartment 2 will lower the electrical potential of compartment 2. Putting them into compartment 1 will raise the electrical potential of compartment 1. What effect will this have on the electrical potential difference across the cell membrane? Well, okay, originally the electrical potential of compartment 2 was 60 millivolts higher than the electrical potential of compartment 1, but now the electrical potential of compartment 2 is coming down, and the electrical potential of compartment 1 is going up to meet it. Okay, so the difference between them is going to get less, basically. So the amount you're going to have to move up when you go from compartment 1 to compartment 2 is going to reduce. So this number is going to become less positive. Okay, so it's going to gradually become less positive, which means we are making a less strong electrical gradient across the cell membrane. Okay, so that firstly is going to stop the movement of sodium ions across the cell membrane, because if we're diminishing the electrical gradient was what was driving the net movement of sodium ions across the cell membrane. So this is one of the factors that's going to reduce the number of sodium ions that we're moving from compartment 2 to compartment 1. But in addition, we've got another thing to take into account, because now there's a chemical gradient across the cell membrane as well, because we've got this concentration gradient. Okay, so we've got sodium ions that are more concentrated here now than here. Okay, so now the point at which you're going to reach equilibrium will once again be the point where the net movement from compartment 1 to the movement from compartment 1 to compartment 2, i.e. the chance of a sodium ion hitting the membrane from compartment 1 side and going through into compartment 2, when that is equal to the chance of a sodium ion hitting from compartment 2 side and going into compartment 1 side. Okay? And the reason these two are going to equilibrate is because if we look at this picture, this movement from compartment 2 to compartment 1 is going to become lower. Okay? And the reason it's going to become lower is because the concentration here is going down because we're moving them out. And in addition, the electrical potential difference across the cell membrane is becoming lower, basically. Okay, so that driving force has gone down. So that's going to reduce down this one, which is why this gets smaller. Meanwhile, this one here is going to become more positive. It's going to become bigger because we're raising the concentration here, which is going to mean the chance of one hitting from this side and going through to here will increase. And in addition, we are reducing the electrical potential difference across the cell membrane. So we're reducing the urge that each one of these sodium ions has to remain in compartment 1. Okay, so both of those things will mean that this gets bigger whilst this gets smaller. So when they are equal, that will be the point that you have a dynamic equilibrium. And it will be before you get down to 0 volts. Okay, so you won't ever get to the point where the electrical potential difference is zilch across this membrane. Okay, you'll get to some lower electrical potential than the original one, and you'll still have a concentration gradient across here. Okay, so that's the concept of an electrical gradient across the cell membrane and how that can also produce change. So within this electrical gradient, you have energy stored. Now, people generally have a better understanding of how you can have energy stored in an electrical potential gradient. Generally, people find it harder to understand how you can have energy stored in the chemical gradient, but look, it's the same principle. It drives change, so it should be considered as having energy stored within it. Okay? Right, and indeed, we can come up with an analogous concept to electrical potential, which is chemical potential. Okay? And basically, chemical potential will be for every single solute. So you'll pick your solute and then you can calculate a chemical potential for that solute. Okay, and this is basically, again, just a mathematical model to help us understand reality. And it's the same principle. What you will do is give to every point in three-dimensional space a real number. Okay, and as I say, it will be specific for the solute, so you'll be talking about a certain solute and you'll be talking about the chemical potential of that solute. So you'll have to do it for every single solute differently, whereas you don't have to do it differently for the electrical potential. There is one electrical potential, whereas chemical potential will vary for the solute. Okay, you just describe to every point in real space a number which is the chemical potential. Now, what does it mean? Well, it's related to the concentration of the solute in that area, but you should just think of it as a symbol that is helping us to understand reality. And that's all that physics and mathematical chemistry and all of that is. It's just using these abstract symbolic structures to understand a pattern that we see in reality, okay? So we use the pattern that mathematicians have created in these symbolic structures, and we say, wait a second, this pattern you've got here is the same as the pattern that I have found in nature, and therefore I can understand the pattern that I have in nature by using your symbolic structure. Okay, and the fancy word for the fact that the structure within the symbolic structure, the mathematical structure, is the same as the pattern that you have in reality is to say that the two are isomorphic. Okay, so there is an isomorphism basically between the mathematical structure and then some sort of pattern within reality. Okay, so that's all this is. It's a mathematical model to help us understand a pattern that we find in reality. Okay, right, and then the idea is that all the points in compartment 1 would have a much higher chemical potential for this blue solute. Okay, and we were assuming at this stage that the blue solute was neutral, okay, because of course we didn't take into account the fact that when these blue solute molecules were moving from compartment 1 to compartment 2, that would change the electrical potential difference across the cell membrane. Okay, but we can get around that by saying we were assuming the solute was neutral, and therefore you were just moving neutral particles, and therefore you wouldn't have changed the electrical potential difference across the cell membrane. Okay, right. So, all of the points in compartment 1 then would have a much higher chemical potential than the points in compartment 2, and then the molecules have moved, well, the solute molecules have moved from compartment 1 to compartment 2 down their chemical potential gradient. Okay, so we'll call it there for this video, and in the next video what we'll do is merge the concept of chemical gradients and the concept of electrical gradients together to make electrochemical potential.